All right, hello physics students. This is Mr. Leaf, and welcome to Chapter 19. We are starting at problem 21 on our practicing physics packet. And for question 21, I've brought a nice picture to give us a visual of this question. It says that you are at rest and you hear the sound of an approaching source having a higher pitch due to the Doppler effect. So that would put you as this person who is on the right side of the police car. You would hear a higher sound because the police car is moving in this direction and it's compressing these waves. This gal over here on the other side, the waves are further apart as she hears them, so the frequency is lower, sounds like a lower pitch because the car is moving again in this direction to the right, moving away from her. So problem A, or part A of question 21, says derive an equation for the speed of an approaching sound source that increases the frequency by X%. So in order to borrow, I want to borrow some from question 19. On question 19, we saw that there was an equation we had that said the frequency of a sound as perceived by an observer is equal to the speed of sound times the frequency of the source that's moving towards them, or rather the frequency of the source that's being emitted, and divided by the speed of sound minus the speed of the source. And in problem 19, we isolated this or rearranged this equation to solve for the speed of the source. And when we did that, we came up with the speed of the source is equal to the speed of sound times 1 minus the frequency of the source divided by the frequency of the observer. So we're going to use this equation then to solve, but we still have to figure out where do we put this X% increase in. Now, I have tried I've deleted this video 3 times because I've been trying to figure out how to explain to you that X% is really what's going on right in here, that percent increase is going on right there. And we're going to express that percent increase as actually a decimal for part B of this problem. I have given up trying to really explain why it is that the X% increase is what's inside this problem. Maybe we can sit down over coffee and hash it out together, and you can help me explain it. But I discovered that that's it. If the X% increase, if it was a 100% increase, then we would then what's inside this parentheses here would be 100%, or the decimal would just be 1.0, and that would mean that the speed of our source was equal to the speed of sound. And so if it were a 0 on the inside of there, 0% would mean that the speed of our source would be equal to the speed of sound times 0, which is 0, and so our source would not be moving. So, and which makes sense. If it's a 0% increase in frequency, the source isn't moving. We're just hearing it like it's being emitted. So anyway, I'm happy to talk with you further on that, but I can't waste any more video time because I've already killed myself trying to figure that out, how to explain that better. So just trust me. For B, what we're going to say is that we have, the question says, calculate the speed of an approaching car whose horn you perceive to be sounding at a frequency 10% higher than its actual frequency. So the velocity of the source, which is what we're trying to calculate, is going to be the velocity of sound times, and then this is where we're going to put in our 10%, but we're going to write it as a decimal and just say 0.1. So really, that's going to be equal to speed of sound is 340 meters per second times 0.1, which is going to be 34.0 meters per second. Now, this is another one of those problems that's dealing with the speed of a vehicle. 34 meters per second doesn't mean anything to us. So we'd be much more comfortable if we could convert that 34 meters per second into kilometers per hour. So we take 1,000 meters in 1 kilometer. Meters cancel out. and then we take 3,600 seconds in 1 hour. Seconds cancel out. And we'll come up with a figure that is somewhere in the neighborhood of 122.4 kilometers per hour for the speed of that car. All right, and since I have you on video here, I'm going to go ahead and I'm going to ask you guys to suffer through with me on problem 23, since it's the last of the problems before the one steps. Okay, so problem 23 says a speedboat makes bow waves as it knifes through the water. And I've got an image here that kind of shows those bow waves that are being produced. So the tip of the speedboat would be, of course, right up here as it's going through the water. We're looking from above the speedboat, and these are the bow waves that are produced. They're kind of producing this angled feature that would look like waves that were trailing the boat behind the water. Now, there's a problem very much like this on page 210 of our physics packet, from which I'm borrowing a lot of several equations, and I encourage you to check that out. That's not in the textbook, but in the actual physics packet. The first question says, what is the angle of the resulting V-shaped bow wave if the boat travels 5 times as fast as the waves on the surface? So what they're talking about here is they want to know what is this angle right here. This angle that's in here. And that angle would be called the Jesus angle, alpha angle. So if we took the total combined angle here, this would be 2 alpha, because that angle is on both sides of the midline of the diagram here. So to figure out that alpha angle, again, borrowing from page 210, it tells us there. Well, really, if I can simplify this, I've got here's 1/2 of that angle. Okay, here's alpha again. Okay, and at any given point in this bow wave here, I'm going to have this distance right here along this axis is going to be the velocity of the source times time. That is to say, the speedboat is going in this direction, and a certain amount of time at any given point in time, that's going to be how far back we were. The velocity times the time is distance. This side right here is going to be velocity, the velocity of the waves that we're talking about times time. That's what this distance is right here. And that is to say that if the disturbance happened right here, that in time t, that disturbance would have carried the waves out all the way out to here. That is, the diameter of the wave would have increased as the wave expanded. Just like starting right here and spreading out and spreading out and spreading out over time t. Okay? So you can kind of see how those waves would spread out in that direction. So the sine of angle alpha is going to be equal to the opposite over the hypotenuse. And in this case, the opposite is going to be Vt over the hypotenuse would be the velocity of the source times t. Now, when you look at that, you can see that you can cancel the t's out, so you're left with the sine of alpha is equal to the velocity of the waves times the velocity, or excuse me, divided by the velocity of the source. So in this problem, they tell us that the boat is traveling 5 times as fast as the waves on the surface. So that is to say that the sine of alpha is equal to the velocity of the waves is 1 compared to the 5 of the source. So if I wanted to solve for angle alpha here, I'm going to take the inverse sine of 1/5. And that's going to leave me with alpha being an angle of about 11.54. If you're not sure how to do that on the calculator, visit me or one of the super smart math kids in our class and show you how to do that. So if that's what alpha is, then 2 alpha is going to be right in the range of 23 degrees. And 2 alpha was what we were looking for. We wanted to know the, they asked us what is the angle of the resulting V-shaped bow wave. Now the second part of the question on 23b says, if the speed of the boat increased, how would what would happen to the resulting angle of the bow wave? So if the boat went in a faster direction that way, what would the result of the bow wave be? So would it be a broader angle like this, or would it result in a narrower angle if that boat were moving with a greater velocity? In order to answer that, we just look at our diagram up here where we saw the velocity of the source times time. That velocity of the source, this is the one that's going right up the middle, right there. So if we were to speed up that source out to there, we know that the relationship between that velocity of the source and the velocity of the waves would change even more. And instead of a sine of 1 over 5, we'd end up with something more like a 1 over 7 or a 1 over 9 or anything like that. And if we take the inverse sine of those numbers, we're going to end up with even a smaller angle than we did with our sine of 1/5, the inverse sine. So the faster that our source goes, the faster our source, the narrower or skinnier our bow wave is going to be. Okay. All right. Well, these two problems are all that I asked you to look at for homework. I'll post another video that when it comes to the one-step problems. All right. Bring these in for tomorrow, Tuesday. Bye-bye.